So, my name is Francisco Cariaga, so I'm here representing TSI Incorporated. We will go from the last presentation and we will change the fluid actually. So before we were talking about water, right? Now we will shift to air. So what is important in air for the pharmaceutical industry. I don't think I will keep you, for so long before lunch, so it's going to be most probably shorter. I don't want to keep you 1.5 hours before going to lunch. So what I will talk about. So we will take a look to this instrument. So this instrument is used for real-time viable particle counter in grade A. So basically in aseptic manufacturing, fill finish. What we will see in the presentation and what are my objective during this presentation. So I would like to give you an introduction first from the basic. We will start how does a particle counter work, okay? So this is an optical measurement, and then we will go through the applications that we have out there with this instrument. We will also touch what is, the guidelines there. So what is in the new Annex 1 regarding this technology. We will also go through the validation of this new technology. So this, and then we will see also the installation. So how does it look in the real world, not in a PowerPoint presentation. All right. First, I would like to have a brief introduction about TSI Incorporated. So we are around since the 60s. It is an American company based in Shoreview, Minnesota. So all our instruments are built in the US, over there. We are close, I would say that now we are close to 1,000 employees with some new acquisitions that we have done over the years, in the last 5 years. And then, as I mentioned, so our headquarters are in Shoreview, Minnesota. And here in Europe, we have 2 main offices. So the first office is our headquarters in Europe, which is located in Germany, in Aachen, very close to the Netherlands. And then we have a distribution and service and calibration center in the UK, very close to London. In addition to that, we have sales offices in France, China, Singapore, and India. So I will not go in much detail, about our mission and vision. I will just say the last sentence here, what is our purpose actually? Well, our purpose is to provide reliable data that we just don't deliver our particle counters, our instruments, so our instruments are part of a big project, right? And also, in that way, we can provide local support when you need it and after sales support. So this is the main reason why we operate with channel partners in different countries. So in Turkey, we have exclusivity with Atotest, and it has been a very successful cooperation. So let's jump into the presentation. I would like to start from the very basic, and explain you what is behind a particle counter. So normally you can see the particle counter there outside. We have 2 of them. But what is, the physics going on there inside? Well, it's not that complicated. Every particle counter use that. So this is a laser light, right? And then we have to analyze a little bit what is the interaction of a laser, a light, with a particle, right? So if we have a laser, then and we have a particle, you see this particle is perfect sphere. So in theory, because there are not perfect things. No. What we have here in this environment are particles that we cannot see, right? They are there, we cannot see them, but they are not perfect. They are not perfectly round. Why then I put a perfectly round particle there? Well, this is the particles that we as manufacturer takes for calibration of particle counters. This is what is called a PSL particles, or polystyrene latex spheres. And they have, let's say, it is the closest particle to the perfect round particle, I would say. And we take those particles, and with those particles we calibrate particle counters. How do we calibrate particle counters? Well, there is an ISO standard for that, and the ISO standard is the 21501-4. In this ISO standard, everything is written for every manufacturer in the world, okay, on how to calibrate the particle counters. It's very important because before that standard, we have seen there deviations up to 20% of counts. So now it's more reliable, so the industry is more reliable, and then every manufacturer has to calibrate the particle counters according to this ISO standard. In this ISO standard, they specify we have to use those particles where certain things are constant. So the material of this particle is constant. So the index of refraction of this particle is constant, right? We use air for the calibration of the particle counters, where we assume as well that the index of refraction of air is constant at certain temperature, ambient temperature. What else is constant here? Well, the wavelength of the laser, right? So this is not changing. As I said before, so we have the laser, and then we will have certain physical effects here. There will be some reflection, as easy mirror, this will reflect here the light. Then we will have refraction that will depend, okay, on the index of refraction. So the light will bend here through the particle more or less according to the index of refraction. There will be some light absorbed by the particle, and there will be also some diffraction of the light. Okay? But if we take this as a constant, we can correlate the size of the particle to the intensity or the amplitude of the signal, of the voltage that we are measuring in an avalanche photodiode, for instance, in an optical detector. So, from that, from the amplitude comes the particle size, right? As you see here, there will be this peak that is 0.3 microns, then 0.5, 1 micron, and so on. Okay, so we have one part. We can know how big the particle is, but then we need to know how frequent these peaks are. And this comes from here, from the frequency, so we are counting all the time here in time, and we can know the particle counts. Okay? So, how does it look in reality? So, it looks like this. So this is a particle counter where we have the laser, this is normally an avalanche photodiode, so a photodetector. And then we are looking the particles that go through this measurement volume here. In addition to that, we need a pump, so we need a vacuum pump that will drag the particles, and the particles will go through this optical device, right? And this is the other part of what you see in the Annex 1, for instance. You have, right? You have particles, certain number of particles, over cubic meter of air. So this is the volume that we are counting, okay? And of course, there are different configurations. We have 1 CFM, so 1 CFM is 28.3 liters per minute, right? We have particles counters like the portables, with 50 liters per minute, with 100 liters per minute, and so on. Why there are different configurations? Well, there are different purposes for particle counters. So normally, I would say mainly two applications. So you can see later on there, we have a portable particle counter. That the portable particle counters normally are used for classification of clean rooms according to the ISO standard 14644-1, right? And there in this standard, they say to you how much volume of air you should sample according to how big is your clean room and what grade is your clean room. Okay? And there comes a flow rate that we have, let's say, 50 or 100 liters per minute to reduce the time of classifying large clean rooms. Why? Because this instrument basically, as you see here, 3 parts, right? So, the first part here is a particle counter. There is no distinction, it's the same, okay? We will understand later on why. Why do we need this part there? And as you see, it's equivalent to our particle counter remote with pump, okay? Or to our portable particle counter fully compliant to 21501-4. Okay? Then we have what we call here a biofluorescent particle counter. Biofluorescent particle counter, so fluorescence. So this instrument is based on LIFT, so that is laser-induced fluorescence. Okay. We will take a look later on in detail how does it work. And finally, I would say as an added feature here, we also have a gelatin filter. This is not manufactured by us, it's by Sartorius. Okay? And this gelatin filter can collect all the particles that are going through this instrument. What for? I will be clear here to try to identify what kind of microorganism was going through the instrument. Okay? The filter has been validated by Sartorius up to 9 hours continuously at 1 CFM. So this instrument works at 1 CFM, okay, so we are fully compliant with the new Annex 1, as well as I mentioned before. It's based exactly as, let's say we have a laser, and then the light will scatter on the same wavelength. This is exactly a normal particle counter. This is the first part. Then, if a particle has attached a bacteria, there are certain molecules in the bacteria that will autofluoresce in a different wavelength. And this is the signal that we detect with this instrument. So, then light scatter and fluoresce of a particle measurement, and then we feed our viability algorithm with this data. So what do we measure? We measure total particles coming from here, and from the viability detector we measure AFU, that is called autofluorescent unit. And the concentration is determined by dividing. So, what is fluorescence? So I'm talking about fluorescence and autofluorescence. Fluorescence is when a molecule absorbs energy from light source, some energy is lost, okay, and the remaining energy will be emitted with another instance. So we are talking about a spectrum of different wavelengths, right? So from here we have the excitation, that is a laser or a UV light, right? And what you get back is a spectrum of different fluorescence at different wavelengths. And this is what you see here, right? So, what is autofluorescence? Well, autofluorescence is when you don't have to add anything to a substance and it will fluoresce by itself. And this is what I was mentioning before. So, if the particle has a bacteria in the bacteria, there are metabolisms or molecules that will fluoresce. So here there is a list, and we list as well the approximate peak of this molecule. Again, it's the peak of the complete spectrum of this molecule that fluoresces. Right? So, if we take a closer look, what is inside the instrument? We will see that. Okay? So this is our viability detector, where we distinguish if the particle is viable or not viable with 3 parameters. So the particle, here is a laser that is close to UV light. So we use 405 nanometers, and as you see, it's very narrow, so it's a laser light. Then we have two photomultipliers that basically scan and see if there is any signal in this bandwidth. We start from 410 up to 500, first scan from there, and the second one, we take a look on the upper part of the fluorescence, from 500 up to 600. So, two parameters, and in addition to that, we have an additional avalanche photodiode there. What is the advantage of that? Advantages and disadvantages. Disadvantage first. Of course, it's a little bit more expensive if you build, two photomultipliers there instead of one, plus an avalanche photodiode. Second disadvantage, of course, you need a little bit more space. What is the main advantage? Well, the discrimination capabilities of the instrument. Why? Because I started my presentation in grade A. So what is the limit in Annex 1 for grade A CFU is 0. Right? If you have one CFU, it's a problem. There's an investigation, a deviation that needs to be closed. So if we put this machine, let's say in grade A, we have to be absolutely sure that it's measuring when it's supposed to measure. Right? And with these three parameters of discrimination, we can assure that much better than other competitors that work with one parameter of discrimination or two parameters of discrimination. So, the application in grade A, actually, in continuous monitoring, field finish, is that basically the machine is always measuring zeros. This should be the case.